Welcome to lecture 3.3. In this lecture, I'll be introducing the molecular orbital explanation of aromaticity and anti-aromaticity by introducing the Frost diagram. I'm going to be presenting a simplified version. This gets the main ideas across without opening the door on the crazy nodes and orbitals. Usually I've seen this not being taught at the highest level, so I think this is a good level to come in at for the Organic Chemistry 2 curriculum. Now, the Frost diagram is going to be built by taking 3 steps. This is going to be similar to the molecular orbitals that were covered in video 2.2 for the conjugated systems, but actually considerably easier. All we have to do is step 1, draw the ring's shape, so that's the skeleton structure, the sigma bonds of the ring, and draw them point down. Then at every vertex, every corner of that shape, we're going to draw an orbital that can hold 2 electrons, and then we're simply going to add electrons according to our standard theory, right? The Pauli exclusion principle and Hund's rule. So let's take a look at a couple aromatic rings and apply those rules. Starting with benzene, a ring that we know is aromatic because that's the aromatic ring. To draw the Frost diagram, what we're going to do is draw the skeleton of the shape of benzene, which is a cyclohexane ring. Then at every corner, which there are 6 of them, we're going to draw an orbital. Note that a little different than before, we actually have degenerate orbitals now. These 2 orbitals and these 2 orbitals, right? There are 2 distinct energy levels that can hold 4 electrons total in each. We have 2 degenerate orbitals. We can call this pi 1, pi 2, and pi 3. And remember, the idea is that anything that's higher than the middle is going to be anti-bonding. So we can say that pi 4, pi 5, and pi 6 are anti-bonding orbitals. With that in mind, right, let's notice really quickly that we had 6 p orbitals going in, right? 1 at every corner. So when we drew a line at every corner, the number of orbitals in is equal to the number of orbitals out. That's a big fundamental rule when it comes to these orbital diagrams. Now dealing with the electrons, we know that we have 6 of them. 6 because we have 3 pi bonds. Filling those in, 1, 2, 3, 4, and be very careful, right? Do not fill in both of these first. We have to fill in the half shell first and then come in with the remaining electrons. It won't be an issue for this one, but you'll see with the anti-aromaticity that it's very important. And that's it. That's the Frost diagram of benzene. If I want to name the HOMO and LUMO orbitals, these pi 2 and pi 3 are my HOMO orbitals, the highest occupied, highest energy filled orbitals, and my LUMO orbitals are here. With that in mind, this explains a bit of the aromatic stability. We see that all of those electrons are placed neatly in stabilized molecular orbitals, and there are no electrons in the antibonding orbitals that are unstable. This is what happens whenever you have 4n plus 2 electrons and you draw a Frost diagram. You're always going to get something that looks like this. Another example of that could be this molecule. As a reminder, it has 2 electrons total and it's fully flat and conjugated, making it aromatic. And again, we don't need to draw the Frost diagram to prove that, but let's draw the Frost diagram anyway. Very important idea, make sure you draw it point down. Right? Did that in red here because it's very important. You do not want to draw it the way it's drawn here, point down. With that in mind, we have 3 orbitals, 3 p orbitals went in, and 3 came out. Right? Drawing a line symmetrically down the middle of the shape, we can see that this is a bonding orbital, pi 1 is a bonding orbital, and pi 2 and pi 3 are anti-bonding orbitals. With that in mind, we can fill in the electrons. We see that there are 2 of them, and they can fit snugly in the bonding orbital. Once again, the Frost diagram, the MO diagram, shows that all of the electrons are in stabilized orbitals, and that means that these rings are aromatic or stable due to their aromaticity. So then what happens with the anti-aromatic rings? Looking at cyclobutadiene, we can finally understand why it's so unstable. Right? Not only is it the weird 90-degree bond angles. So we see 4 orbitals there, fully conjugated flat ring. However, it has 4 electrons, which fits the 4n rule, meaning it's anti-aromatic. Remember, we have to draw the shape point down when making a Frost diagram. We can draw orbitals at every point. And now we have these orbitals that are in the plane here, which makes them non-bonding. we have stabilized bonding orbitals down here and destabilized orbitals up here. Excellent. Now that we've set up our Frost diagram correctly with the orbitals at every vertex and our point is down, we can fill in the 4 electrons. And look what happens. So these 2 electrons, the first 2 enter the nice stabilized bonding orbital, but then something interesting happens. Because of the Pauli exclusion principle, because we have to separate the half shells first, this is actually where we have to stop with 4 electrons. And what's interesting is, well, we don't have electrons in an antibonding orbital in this case. We have 2 different unpaired electrons. If you recall from introductory OChem, an unpaired electron is referred to as a radical. So an anti-aromatic ring, that is, any ring that is fully flat and conjugated and has 4n electrons in its system, is actually described as a diradical. Right? Radicals are not known for their stability. And so being locked in a ring means that this conjugated system is actually bad. It can't get out of its conjugation. It is a conjugated system, but it's a conjugated system that results in a diradical character, which is incredibly unstable. This is going to be true for any ring that has 4n number of electrons and is fully conjugated. As another example, let's take a look at this one we previously called anti-aromatic. 5 carbons, we draw it point down, an orbital at each side, at the middle of the shape, somewhere around there. So we have 3 bonding orbitals and 2 anti-bonding orbitals. Considering this, we can fill in the number of electrons. We once again have 4. 1, 2, 3, and 4. And look at that same pattern again. Anti-aromatic rings are incredibly unstable because of this diradical character, and the Frost diagram is a great tool to demonstrate that. Once again, these are the HOMO and LUMO orbitals. That doesn't change. Right? That's definitional. So with that, hopefully now you can use Frost diagrams to explain using MO theory why aromatic rings are so stable and why anti-aromatic rings are so horrible. In our last video, I'm going to cover how we can handle lone pairs in aromaticity, as there's a little bit of a complication with them, and then we can move on to the reactions of aromatic systems. I'll see you there.